Okay. My title is Affine Kac-Moody groups as twisted group groups. And our talk is divided into two parts. Part one is here. I will talk about joint research with Professor Jun Morita and Professor Arturo Piazzolla based on recent papers here and here. And then I'd like to have a question time here. And then part two, Jun will give a talk about some photos. Okay. So, okay, let's start. So this is an introduction. Okay. Let's we give a finite dimensional simple real algebra G like this. Then Shibata constructed a group, or I should say group scheme. Now it's called Shibata group of simply connected type. For example, if we take G as SLN, then we get large SLN, something like that. Okay. And we already know that there is a good generalization of these guys into infinite dimensional setting called Kac-Moody algebra, which is determined by generators and relations. Okay. And then in this setting, we also construct a group called Kac-Moody group. And we shall write, I shall write G hat in this slide. Okay. So this is a small history about Kac-Moody group. First of all, Peterson and Katz constructed a Kac-Moody group over a field of characteristic 0. I think this is the first time. And then Titz studied Kac-Moody groups as not only an abstract group, but as functors defined over rings. Okay. So if we take G hat as an untwisted affine Kac-Moody algebra, then it is easy to show that the corresponding Kac-Moody group here, Kac-Moody group, are realized by groups, or I should say algebraic groups. Right? So today, our main today I would like to do the same thing for a twisted case. I would like to control G hat for twisted affine Kac-Moody algebras by using known objects like this. Okay. So before that, we shall see what is the Kac-Moody group, the definition of a Kac-Moody group. Okay. Okay, let small G hat be a Kac-Moody algebra defined over the complex number field C. And we shall write this symbol, the set of all real roots of this guy. Okay. And this is a little bit technical notation. For real roots A hat, then the pair X A hat and X minus A hat taken from A hat root space of G hat and minus A hat root space of G hat is called a Shibata pair if these pairs satisfy these two relations. Here, omega denotes the Shibata involution, and A hat check is the co-root. Then we can easily show that this relation holds. Okay. So now let's take K to be a field. Sorry, we have to take a space here. Let K be a field in general. And let's take rho is the representation here. Here V denotes the direct sum of these guys. Here lambda I denotes the fundamental weights. So we take such a natural representation. Then we can define for all real roots and scalar U, we can define this infinite sum. Because this is integrable, so the sum is not infinite. So we can consider such elements in V, automorphism. So I denote this guy X A hat U of U. Okay. So what is Kac-Moody group? Yes, the Kac-Moody group is, I should add a simply connected Kac-Moody group G hat defined over K, or a little bit long name, associated with G hat is the subgroup of automorphism of V generated by these objects. The definition is quite simple. Okay. So, but there is another definition of Kac-Moody group. So I will give its result. So in 1987, Tits determined its generators and relation of Kac-Moody group in general, considered as a Tits functor defined over ring. Moreover, he shows the functor is unique over our field. If we work over field, then such a Kac-Moody group is somewhat unique. And he also showed that this inside of G, then simply connected, of course, then there these four relations holds. These are the determining relations of G has. Here W denotes the reflection as usual, and H is an element of a torus. Then first is maybe obvious. Then second, this B is explained about the commutator relations of XA hat of U and XB hat of V. Here, see something is just a scalar. Yeah. Here, B hat denotes B hat is the relation about the reflection. Here, eta is the sign, and C is the torus relation. But we do not use these relations seriously in this talk, so please forget. Yeah. Okay. So in this talk, we concentrate on the affine Kac-Moody algebras. So we shall denote affine Kac-Moody algebras, this symbol. Here, X denotes the type of thinking diagrams. Here, A, B, C to D. And this R denotes the tier number of the thinking diagram. So if we take one, then the affine Kac-Moody algebra is called untwisted. Otherwise, such affine Kac-Moody algebras are called twisted. So please note that 3 only occurs when we consider X equal to D4. So something like this, okay, D4, and we consider such case. Okay, so R denotes the tier number. Okay, and let just small g denotes the finite dimensional simple real algebra of type this Xn, and denotes delta is its root system for fixed certain pattern subalgebra G. So first of all, we shall consider the case when R equals to 1. So this is untwisted case. This is somewhat simplest case. Okay. So now let Lz be the tensor of G and Laurent polynomial ring, and this is often called loop algebra of G. Okay. Then one gets the following this exact sequence. So this means that G hat prime here prime denotes the derived reserve algebra of G hat. So we can get a central extension of G hat. Okay. So if we want to know this guy in untwisted case, then it is enough to study group algebra. this exact sequence tells us that. Okay, so we want to lift up this sequence to the group level. Okay? Group level. So let G hat denote the Kac-Moody group over defined over a field K of type X and of 1. This means this is a Kac-Moody group associated to G hat equals to G hat X and 1. Yeah, this means that. And this G, okay, in my slide, there are many G's here. Okay, here is G, of course, here is G, and this one is G, this one is G. But so I should pronounce differently. So this guy should pronounce small g, and this guy is large G hat, and this guy is wow, fractal G. Okay, so anyway, so this fractal G denotes the Shibata group scheme of type Xn. Actually, this guy defined this Shibata group scheme defined over Z. Okay, so yes, here this fractal G is a group scheme. We can put LG to be this form, the Laurent polynomial ring valued point of G, fractal G. Okay. Here X, K Z plus minus is the Laurent polynomial ring over our field K. And this guy, LG fractal G, is called algebraic group of G. So this is quite easy example. If we take G to the SL2, I mean, if we take X and R to be A1, 1, then the fractal Z is just SL2, and the group is just these 2 by 2 matrices. Here, the entries are all entries are Laurent polynomial ring and satisfying determinant equal to 1. Okay, this is just an example. Okay, so then okay, here this is just a notation of yes. For the affine Kac-Moody algebra case, the real roots can be write down explicitly like this: alpha plus and delta. Here delta is the null root. Okay, so and by definition, G hat, our Kac-Moody group, is generated by such guys. Yeah. And there is how to say central extension of G hat. So if we in this case we can write this map explicitly. I mean this map is given by this formula. Here x a plus n delta belongs to this set, and then it goes to x alpha and z to n. Right? Very quite simple. Yeah. Sorry. Here x something denote the separate elements, separate pair or separate elements. Okay. So using this fact, then we get this group homomorphism here, the Kac-Moody group to the loop group. So here x alpha plus n delta of u goes to x alpha of u z to m. Here we have defined this guy to be this set. So this guy belongs to here. Okay, so in this way we get this central extension. Okay, this result is known by Peterson Katz, and also see the Garand's famous book. Okay, this is untwisted case. The correspondence is very similar, and there is no doubt here. So this is very clean, I think. So our main focus is how is this for the twisted case. So let me explain some notations. So next week, focus on the case of twisted case, equal to or 3. Okay? And then we take a non-trivial linking diagram automorphism of order R, which is denoted by sigma, and also take algebra automorphism here, this Laurent polymer ring to this Laurent polymer ring. This tau maps here this element to this guy. Here, zeta is a fixed R's primitive root of unity. And then we define LG sigma, a new object, LG sigma, to be this guy. Of course, LG is just a G tensor C plus minus 1. So this, as a vector space, this is just G tensor this Laurent polynomial ring. So we can fix G and tau simultaneously. So this guy, we shall call this guy twisted loop algebra of G. Then, as we can see, this LG sigma naturally form a real algebra over here, the base ring, Laurent polynomial ring, and satisfies this Galois-Descent formalism, this one. Also, we can define or how to say study more concretely. I mean, here LG sigma is just a direct sum of this guy and this guy, and here Gn is defined by how to say this space. Yeah, maybe this is more familiar, I think, but we want to think this guy as a Galois-Descent object. So we prefer this formation. Okay, so this is a problem. So in our twisted case, we also get the following exact sequence. This is, of course, very known thing. Yeah. So the central extension. So if you want to know this guy, then it is enough to study this twisted loop algebra. Okay. So our purpose is this. Again, we want to lift up this sequence to the group level. Of course, this guy is just a Kac-Moody group, of course. And this guy is just a one-dimensional multiplicative group. But we do not, at least this time, we do not, what is this? What is this? We have to define such corresponding group. So what is this? So the problem is, what is twisted loop group? We haven't defined it yet. In this talk, we haven't defined it yet. And how can we define that? Yes, this is the problem. And there is a solution. This is one solution. Use the notion of twisted Shibata group. Twisted Shibata group over rings. Okay. In the Steinberg's book, there also a notion of twisted Shibata group, but it's as far as I know, it's just defined over a field. So in our setting, we have to how to say generalize such defined over rings, because we want to use Laurent polynomial ring. So, but this was already done by Professor H. Abe long time ago. This paper. So we use the result and construct such guy and this map and show that this is split. This is ancestral extension. This is a strategy. So let's see what is twisted Shibari group over defined over ring. Okay. Okay. Equals that this small g is a finite dimensional simple Lie algebra of type xn, and fractal z is the Shibari group scheme associated with g. And I'd like to write z fractal g, yeah, here denotes the coordinate ring. I mean the Hopper algebra over z. Okay. Now first we take a Shibari base of g like this. Here x alpha is the Shibari pairing, and hi denotes the base of Cartan subalgebra of g. And then we can find a z form of g. Okay, so then the linking diagram automorphism sigma induces an automorphism of gz to gz. So z form, we can restrict it sigma to the how to say the word of the integers. So something like this. Okay. So then there is a Hopper pairing. Here you denote the universal M-pairing algebra of ZZ, and using this Hopper pairing, I mean here sigma is act on here, so we can translate the sigma action into the coordinate ring ZZ like this. We can get a Hopper algebra automorphism. So in group theoretic term, we get a group automorphism here to here. Here, this guy goes to sigma alpha and plus minus u. Here, this sign is just correspond to this one. Anyway, we can find such automorphism. So then let's fix the algebra S, and we can identify the S point of this fractal Z with the algebra map from the coordinate ring of G. Oh, sorry, to S. So still, I don't know how to write down this symbol. Maybe this guy. It is very hard for me. Yeah. Anyway, so we identify the S point of fractal Z with the algebra map from here to here. Okay. Then we take any algebra automorphism tau here with order R. This is the same. The R is the order of sigma. Then we can consider the fixed point subgroup like this. Here G equals to sigma G tau like this. So and this this fixed point subgroup is called the twisted Shibari group over S with respect to these two guys, sigma and tau, which are called. Okay. So let me give some example. If we take xn equals to a to 2, I mean BC type, or I should say, then the Shibari group is nothing but SL3. Then the twisted Shibari group over S is the your like is an arbitrary Z algebra. Yeah, the twisted Shibari group is given by this this set SU3S. Here TX denotes the transpose matrix, and J denotes this guy. and X bar denotes this guy, these matrices. Okay. So this is an example of twisted supergroup. So we can find what is twisted group. Okay, let me give the precise definition. Okay, let us return to our situation. Okay, let K be a field of characteristic not equals to R, the entire number. So R takes 2 or 3. Okay, and here is the technical assumption. Here, the technical assumption. Here, zeta denotes the R's fixed R's primitive root of unity. So if R equals to 2, then there is no assumption. But if we consider D4 case, D4 case, then at least in this talk, we have to assume that this primitive root of unity belongs to our field K. But in our paper, this assumption is no needed. Okay, now and set S to be the Laurent polynomial ring as before, and the tau denotes the automorphism defined by this formula. Yeah, and so what is twisted group? The definition is just this: the twisted Shibata group of S with respect to this sigma and this tau. Yeah, this is the definition of twisted group. Okay, so the definition is a little bit how to say complicated, but still we can find its generators. So using Brewer decomposition, or I should say Euclidean algorithm, yeah, we can write down generator of the group, this group, explicitly. Yeah, the result is this is just coincide with elementary subgroup of this guy. Anyway, so for example, the previous case, previous example, if we take this, if we take xn to the BC type, then a twisted Shibata group is nothing but SU3S, and using Euclidean algorithm, we can show that this group is generated by these elements. Yeah. So looks like a little bit complicated, but still we can write down the generators explicitly. Yeah. Okay. So our main motivation is this. What was this? So there is a central extension in the Lie level. So we want to lift up the central extension to the group level. Okay. So let me so the of course there is a Lie algebra surjection here from here. Sorry, wow, here to here. Oh. Okay, here to here. So it is easy to show that this Lie algebra surjection induces a group homomorphism from Kac-Moody group and our twisted group. Okay. So this is somewhat like here, but actually, or how should I say, honestly speaking, this is just alike. So if you want to write down explicitly, then there is a lot of case by case consideration. Okay. But still, we can define such map, and also we already write down generators explicitly, so we can show that this is surjective. So to show the surjectivity of this map, we have to know the the generator of this guy. Yeah. But we already done. So this is we can show that this is surjective, and its kernel is contained in the center of Kac-Moody group. This is the easy part. And moreover, we can show that this kernel is one-dimensional. So as a consequence, we can show that using this twisted loop group, we get this short exact sequence, central extension. So in the twisted case, if you want to the Kac-Moody group, then it is enough to study the twisted loop group LG sigma. Yeah, this is one of the main results of our research. Okay, so next is Galois action. So for simplicity, let S denotes the Laurent polynomial ring of this guy, and R denotes the Laurent polynomial of this simple guy. Then we can consider Galois group of this ring extension, and we can show that the tau is a generator of this group, and our assumption, here, this is our assumption, gives this, sorry, how should I say? The gamma is isomorphic to Z over RC. But anyway, then next we consider the following this group homomorphism from Kac-Moody group of untwisted guys to the S point of Shibata group, like this. Here, alpha hat denotes the real roots. Yeah, this is a natural map. And on the other hand, the Galois group acts on untwisted Kac-Moody group by this formula. Then we can show that this phi is compatible with the Galois action gamma. So we can take a fixed point functor both sides, and then we get this guy, phi gamma. But this is just a definition. This guy is a twisted loop group or loop group. So we get a fixed point subgroup to the loop group. Okay. So what we done? Okay, we also construct a natural map from here to here. So we get this exact sequence. So this is the map, our main theorem, and this is a fixed point functor. And we can show there is something like boundary map from here to here, and this is commute. So this should be isomorphism. Yeah. So as a corollary of our main theorem, we can show that the fixed point of untwisted is isomorphic to twisted Kac-Moody group. This is just a corollary. Okay. So the picture is so simple, I think. Okay, now let me talk about the scheme level. So let F be a prime field of characteristic not equals to R. Our R is the tier number 1 or 2 or 3. Yeah. Then and assume assume the parameter R3 due to U of unity belongs to our base field F. F for simplicity. So again, we can drop this assumption, but in this talk we assume this for simplicity. Okay, and let R denotes the Laurent polynomial ring and S to be this guy, and large A is the coordinate ring of this fractal R. Then the lower group, gamma, also acts on the tensor over RLS as a Hopper algebra automorphism like this. So here A is this guy. So our symbol should be sigma, okay, and S should be tau. Anyway, so there and there is an action of gamma. Okay, so we can consider its fixed point, and we shall denote it by a hat. Okay, and we defined G hat to be the corresponding group scheme. Since this one is Hopper algebra, so the corresponding one is group scheme. Okay, so by construction, we can show that this isomorphism holds. So this is Galois descent formalism, and we can show that this theorem. So one is its Laurent polynomial valued point is coincide with the Kac-Moody group over one-dimensional one-dimensional counter as groups. And moreover, we can show that the kind of Lee's-Third theorem. So if we, since this is a scheme, this guy is a scheme, we can take its D algebra of this guy, and if we detect its Laurent polynomial link varied point, then that one coincides with this. Yeah. Okay. So this is our main, the second main result. Okay. So my talk is here. This is the last slide. So happy birthday, Professor Moody. Yeah, this is my memory. Here, this picture is taken at 2013 at University of Tsukuba. Yeah, this is my first time to met with Moody. Yeah, Professor Moody. Yeah, here Jun and Professor Shigeki Akiyama here. I'm here. When at this moment, I was a PhD co-student. So this is very fantastic time at that time. So, and this is another picture. Here is recent picture taken at University of Alberta. Yeah. Here's selfie. And this is I and Arturo and Professor Moody. Yeah. Okay. Yeah, my talk is all right. Yeah, thank you for your kind